In this video, we're going to discuss some basic facts about images and preimages. So let's let f be a function from a to b, and s be a subset of a. Then the image of s under f of x is the set of all y in b, such that there exists an x in s, such that f of x is equal to y. So first, a theorem, let f be a function from a to b, then the image of a under f is equal to the range of f. All right. So recall that the range of f is defined to be the collection of all b and b such that there exists an a and a such that f of a is equal to b. That's how we defined the range. Now if we apply the definition of the image of a set to the image of all of a, we get the image of a under f is the set of all y and b such that there exists an x in a such that f of x is equal to y. And that those two definitions clearly define the same set, just with slightly different notation. All right. So that proves that f of a is equal to the range of f. Another theorem, for any function f from a to b, the image of the empty set is equal to the empty set. So according to our definition of the image of a set, the image of the empty set would be the set of all y in b such that for some x in the empty set, f of x is equal to y. Now of course, given a y in b, there's never an x in the empty set so that f of x is equal to y. So no y in b is eligible for inclusion in f of the empty set. That is, the image of the empty set under f is empty. Let's let f from a to b be a function and t be some subset of b. Then the preimage of t under f is the set of all x in a so that f of x is in t. All right. So it's a set of all x in a so that f maps x to an element of t. So first theorem, if f from a to b is a function, then the preimage of the codomain is the domain. In other words, the preimage of b is the domain of f. Well, recall that the domain is the set of all a in a such that for some b in b, f of a is equal to b. Now let's apply the definition of the preimage to the codomain b. Okay, the preimage of b under f is the set of all x in a so that f of x is in b. All right. Now to say that f of x is in b is exactly the same as saying that there exists a b in b such that f of x is equal to b. All right. In other words, these are clearly again the same sets. These two are just two different ways of writing the same set. Another theorem, if f from a to b is a function and t is a subset of b, then the preimage of t has to be a subset of the domain of f. It's easy to see, so the preimage of t is the set of all x in a so that f of x is in t. If x is some element of the preimage of t, of course that means f of x is in t, and t is a subset of b, so f of x is in b. All right. So since f of x is in b, that means if x is an element of the preimage of t, there is some b in b so that f of x is equal to b. Okay, that's just another way of saying that the function f is defined at x. In other words, x is in the domain of f. All right, so the preimage of t is a subset of the domain of f. The preimage of the empty set is the empty set. So the preimage of the empty set would be the set of all x in a so that f of x is an element of the empty set. Of course, there are no elements in the empty set, so for any x in a, f of x is not an element of the empty set. So there's no x in a so that x is in the preimage of the empty set. That is, the preimage of the empty set is empty. Okay, the last theorem we want to prove has two parts. If f is a function from a to b, and s is a subset of a, and t is a subset of b, then first, if s is an element of s, then f of s is an element of the image of s under f. And if s is an element of the preimage of t, then f of s is an element of t. All right, and in fact, that last one's if and only if. So s is an element of the preimage of t if and only if f of s is an element of t. So first we'll prove that if little s is an element of the set big S, then f of s is an element of the image of s under f. So let's let f be a function from a to b, and s be a subset of a. And let's suppose that s is an element of the set S. Consider the value t, which is the value of f with input s. Okay, so clearly t is an element of the image of s under f. Okay, the image of s under f is a set of all y and b such that there exists an x in s so that f of x is equal to y. Okay, and clearly t satisfies that definition, namely f of s is equal to t. All right, and so that exactly means that f of s, which is t, is an element of the image of s under f. Okay, so it really is just a restatement of the definition in a sense. So now we'll prove that s is an element of the preimage of t if and only if f of s is an element of t. So again, let f be a function from a to b, and t be a subset of b. First, suppose that s is an element of the preimage of t. Now, of course, that's the set of all x in a so that f of x is in t. And that exactly means then that f of s is an element of t. Okay, if f of s is an element of t, on the other hand, then s is an element of a with the property that f of s is in t. And so, again, by definition of the preimage of t, s is an element of the preimage of t. All right. So these two little theorems here are just kind of restatements of the definition of image and preimage. Now, a couple of important points. The first part of that last theorem said that if f is a function from a to b and s is a subset of a, then it's true that if s is an element of the set S, then f of s is an element of the image of s under f. But the converse of this statement is not true. Okay, that is, if you know that f of s is an element of the image of a set S under f, then you cannot conclude that s is an element of s. Okay, so for example, consider the function from the reals to the reals defined by f of x is equal to x squared. And consider the interval 1, 3. All right, so suppose s is the interval 1, 3. F of s is the interval from 1 to 9. F of negative 2 is equal to 4, and that's an element of the image of s under the function f. Okay, but negative 2 itself is not a member of s. Okay, so this example here shows that it is not true that if f of s is an element of the image of the set S under f, then little s is an element of s. All right. Another warning here, if f is a function from a to b and t is a subset of b, if t is an element of t, we cannot say that f inverse of t is an element of the preimage of t, of the set capital T. All right. Now the reason we can't say that is we can't even write f inverse of little t unless we know f of x is bijective. Okay. In other words, f inverse of t, that notation means the preimage of the set T. That's always defined. But you cannot stick, if you say f inverse of little t, like an element of the set B, then you are assuming that the inverse of the function f is defined, and it may not be. Okay, so you just have to be careful. The preimage is always defined, but the inverse of the function is not always defined. And so that notation of f with a -1 superscript, you should always take that to mean preimage unless you know the function is invertible and you know f inverse is the inverse of the function. Right? The preimage of the set containing t always makes sense, but f inverse of t only makes sense if f of x is bijective. Okay, so that's another instance of that warning. All right, that's it for this video. Thanks for listening.